Welcome everyone to slide 39, the study of nitrogen nucleophiles. With this slide, we're going to talk about under acidic conditions, aldehyde and ketones react with a primary amine to form an imine. We can see that right there. Good example of the imine formation. We're going to see that on the next slide, but you can also look at page 860. And an imine is a carbon doubly bonded to a nitrogen. You can see this right here. So here we have this aldehyde, right? And we convert this to an imine. And we're going to go over how this is done. So first, you're going to have a nucleophilic attack. So the imine attacks the carbonyl group. And then we have a proton transfer. We have a second proton transfer here. And that lone pair of electrons goes on this nitrogen. That kind of makes sense because this is electrophilic. It wants some electrons. It has a positive charge. Then we have this carbonyline. Then we have another proton transfer. We're creating a good leaving group right here. So you want to create a good leaving group. So we create our good leaving group. We know water is a good leaving group. So now we're going to have the loss of our leaving group. And then we're going to form an imine. So our first three steps, step 1, step 2, and step 3, it was all to form this intermediate right here. So this is to form this carbonylamine. After this, our next 3 steps are going to form our imine. So notice that the first 3 steps of here are very similar to the 3 steps of the acetyl formation, but the order of the steps has changed. So the imine formation begins with a nucleophilic attack, while the acetyl formation begins with a proton transfer. So those are your big differences. So it says, even though it is under acidic conditions, pronation of the carbonyl is not the first step of the imine formation mechanism. Amines are bases and consume the proton catalyst. The ammonium ion is the acid catalyst for the reaction. So the ammonium ion is not acidic enough to pronate an aldehyde or ketone, but it is acidic enough to transfer proton to the negatively charged oxygen in the second step. So that's a big deal right there. So for imine formation, the pH has to be right around 5, or the reaction is too slow. You can see they found the optimum rate right here. What they did was they done a bunch of different experiments. They probably done one at 1, 2, 3, 4, and they probably did some in between. So a bunch of different experiments. They figured out what the optimal pH was for the highest rate. So if you have a higher pH, there's not enough acid to catalyze the reaction effectively. At a lower pH, all the amines are pronated, none are available to attack the carbonyl. So under acidic conditions, aldehydes and ketones react with a secondary amine. So we have a secondary amine because you have, it's bonded to 2 carbon groups right here, 1, 2. Reacts with a secondary amine to form an enamine. So here's your enamine right here. The reaction requires acidic conditions to work. The mechanism is identical to the amine formation except for the last step. Let me show us the so let's just take a look at the amine formation. So it says it's different from except for the last step. For the last step we see we had a proton transfer for the amine. So if you can just imagine, you know, we go back here, just take a screenshot of this. So we're deprotonating the nitrogen right here. It's a proton transfer. Here we're not taking the proton off of the nitrogen here, right? There's no proton to take it off of here. So we're creating this double bond right here. So first we have our nucleophilic attack, that's the same. We have 2 proton transfers, same step. So we have step 1, 2 to 3 to get to the same intermediate. We're creating a good leaving group, but the thing is we don't have a proton transfer step right here, you know, because there's not a proton to grab right there. We're grabbing it from right here, so then we're creating an enamine. So enamines are compounds in which the nitrogen low pair is delocalized by the presence of an adjacent carbon-carbon double bond. A mechanism for the so we see the mechanism right here. And this is in equilibrium right here. You know, this step is in equilibrium. Where, you know, this can come back here and come back here. So we're in equilibrium right here. So the reaction requires acidic conditions to work the mechanism. Here we're forming our imine, and here we're forming our enamine. When we come to this Wolff-Kishner reduction, which is a 2-step synthesis converting a ketone to an alkane. So here's another mechanism where we can convert a ketone to an alkane. So the first step is the imine formation between the ketone and the hydrazine, which is like a primary amine. The second reaction is like an elimination. So, you know, the book says that this transformation has practical utility because hydrozones are readily reduced under strongly basic conditions. So here is the mechanism of the Wolff-Kishner reduction. Note how many proton transfers you have. 1, 2, 3, 4. And also note right here, what is the leaving group that's being lost? Well, it's nitrogen gas, right? So you're losing N2 gas. That means we're not going to be in equilibrium. You know, if this is gassed off, this is going to leave the reaction. So we're going to be going this direction right here. So we have our first proton transfer for one of the protons is removed, forming a resonance stabilized intermediate. Then you have another proton transfer, followed by a third proton transfer. Now we have our great leaving group. I'm going to call this the great leaving group. Then we're going to form our carbanion. We have our carbanion right here. and it wants to be protonated. So, we're going to have a proton transfer from water, and we form our alkane. So the yields, because of the nitrogen gas loss, are usually very good. So I'm just going to leave that up there so you can take a look at it. All right, so are there any questions regarding the Wolff-Kishner reduction? Okay. So note that there are many similarities between the acid catalyzed mechanisms that have been discussed. One thing to always note is under acidic conditions, reaction species should either be neutral or have a +1 formal charge. And we can see that here. So then they go on to the study of hydrolysis of acetyls. So acetyls are hydrolyzed with aqueous acid to yield a ketone. So we have our acetyl here. Remember, this is not a hemiacetyl. This is an acetyl. It has two R groups. So simply the reverse of an acetyl formation. We add a proton. And we get this ketone right here. So we have our ketone plus 2 alcohols. Oh, sorry about that. So acetyls will only react with water under acidic conditions. So that means if we put it under basic conditions, there's going to be no reaction here. So let me come right back. I have my dogs barking, so just give me a minute. All right, so let's get back to our study of hydrolysis of acetyl, the acetyl mechanism. And I just want to point where you can find this mechanism at. If you go to page 869, you're going to be able to find this mechanism. Oh. So, let's go over it. So we have a proton transfer here. Then we have the loss of a leaving group. So the molecule of alcohol is ejected as a leaving group. So we have an alcohol here. You can just imagine some alkyl chain. We have a leaving group. Then we have, we have a nucleophilic attack, followed by another proton transfer. Now we have this hemiacetyl. So the hemiacetyl is just this RO group with this OH group right here. And this is called your hemiacetyl. Then the other ROR group right here is going to have a proton transfer. So it's going to become a good leaving group. So we get our second alcohol group gone right here. So our first alcohol group was gone here. Our second alcohol group is gone here. We have another proton transfer, and then we finally generate our ketone. So we went from an acetyl down to this ketone group. So notice that the acetyl hydrolysis proceeds by a hemiacetyl intermediate. So in fact, all the intermediates involved in acetyl hydrolysis are identical to the intermediates involved in acetyl formation, but in reverse order. So hydrolysis of amines and enamines undergo a very similar mechanism under acidic conditions. And basically note that if you have these conditions, you're going to form the ketone. So the mechanism of hydrolysis for amines and enamines is simply the reverse of the mechanism of formation. So now we get to the study of sulfur nucleophiles. So now we're looking at, instead of OR groups here, remember we're looking at with the acetyls, these are oxygens. Now we're looking at sulfur. And note that sulfur is just one down from oxygen. But ketones and aldehydes react with thiols virtually the same way. Well, that kind of makes sense, right? Because oxygen or sulfur is just one down from oxygen on the periodic table. And we're going to form our thioacetyls, and then we're going to form our cyclic thioacetyls. You know, we can just imagine that it's kind of the same mechanism with oxygen, just with sulfur now. So why do you think they do this? Well, they put these on as protecting groups, you know. This is a protecting group right here. So thioacetyls can be converted into alkanes. You can also convert them into alkanes. So if we use this compound called rainy nickel, we'll take this thioacetyl into an alkane. So rainy nickel is a spongy nickel. It's a fine grained solid composed mostly of nickel derived from a nickel aluminum alloy. And so it's a light gray powder. So the molecular form of rainy nickel is aluminum nickel. So now we have another mechanism for reducing a ketone or aldehyde to a corresponding alkane. Our next study involves the hydrogen nucleophiles. Remember our lithium aluminum hydride? Sometimes I don't know why they wrote LA. I've always seen it like this, but this book likes to do it like this. But anyways, this is a good hydride source. Sodium borohydrate. So, you know, we have a good hydride source. We can knock that ketone out. So as these reductions are carried out under basic conditions, hydrides are strong nucleophiles. Yes, they are very strong nucleophiles. And they show it to you right here. So we have a nucleophilic attack. And generally, I just show it like this, but it is on that aluminum right there, followed by a proton transfer. And we generate our alcohol. And then the next study, okay, so they're talking about chiral centers. So recall reduction of an unsymmetrical ketone forms a new chiral center. So we have a racemic mixture, right? Because this is an sp2 hybridized carbon. You know, the hydrogen can either come in from the top side, I'm trying to do this the best I can, or from the back side. So I'm going to call that the back side. It can come in from the front side. Now, depending on where it comes in, if it comes in from the back side, it's going to push this oxygen to the front. If it comes in from the front side, it's going to push the oxygen to the back. And we get a racemic mixture of R and S. So this would be big, big, big. So this would be S. This must be R then. So we have carbon nucleophiles. So we're talking about hydrogen nucleophiles. So carbon nucleophiles, we've mentioned this already. This is just your Grignard. We have this carbanion come in like this, have a proton transfer. That's why they have the water right there. And we can form this group. We also get a racemic mixture right here, where the carbanion can come from the top or if it come from the back side. It says, note either face of the carbonyl is attacked by the nucleophile and a new chiral center may result. And I show that right here, the nucleophilic attack followed by a proton transfer. Then they talk about this reaction with hydrogen cyanide. So cyanide ion is also a carbon-based nucleophile and reversely adds to ketones or aldehydes to form a cyanohydrin. You can just imagine this right here. It's a carbanion. And it's going to come in here like that. So this reaction works better under basic conditions. And so a catalytic amount of base is usually used. So in the first step, a cyanide ion attacks the carbonyl group. We saw that right there. And the resulting intermediate then abstracts a proton from HCN. So we have some HCN, right? It's going to take a proton. That's how you form this group right there. The process is reversible and the yield of the products is therefore determined by equilibrium concentrations. Unless you can see that right here. So acid workup is not necessary since the HCN serves as a source of protons. So once we have that, let me see if it actually shows it in the PowerPoint slides. It does. To achieve basic conditions, KCN is usually added along with HCN. And this way there's more cyanide than protons. So new chiral center is possible in this reaction as well, and they show it right here. I wanted to get to the next slide because from this slide right here, we see this, cyanyl group right here. And that can effectively be a good leaving group. Now, remember, lithium aluminum hydride is a good nucleophile. It comes in here like this. Well, this is going to take off then. But in this case, they're going to convert it into another functional group. Let me see. So in the first example, the cyanyl group is reduced to an amino group. So we're going to reduce that to an amino group. So sorry about that. We're just going to reduce this right here to the amino group with this lithium aluminum hydride. We're not going to attack it right there. We're going to attack it. We're going to make it so that it's going to become an amino group. And we have our amino group right here. Maybe how we could do this, or think about this, if we can come in here, this will come in here, and we just protonate it. So that's one. Now let's do it again. So now we have our amino group right here. So we formed our primary amine. We can also generate the carboxylic acid by throwing acid and heat at it. Then they talk about this Wittig reaction, which George Wittig, a German chemist, was awarded the 1979 Nobel Prize in Chemistry for his work with phosphorus compounds and his discovery reaction with enormous synthetic utility. So it has had a big industry utility. It basically converted this ketone into an alkene. You're converting this ketone into this functional group right here, into an alkene. A carbon-carbon double bonded to each other. I said the Wittig reaction is a phosphorus ylide in which a carbon atom acts as the nucleophile. An ylide is a neutral compound that contains a negatively charged atom adjacent to a positively charged heteroatom. So that's the definition of an ylide. So an ylide is a neutral molecule that contains a negatively charged atom. In this case, it's going to be carbon, directly attached to a positively charged heteroatom. So okay, our negatively charged atom. Here's our positively charged heteroatom right here, the phosphorus. It says the mechanism is like a 2+2 reaction, cycloaddition. And they show us a good example on the next slide of this 2+2 cycloaddition right here. So this generates an oxyphosphatane, and the oxyphosphatane decomposes to produce an alkene and a triphenylphosphine oxide. So here, this is where we're forming our double bond right here. And we have this right here. So the formation of the specially stable triphenylphosphine oxide byproduct derives the equilibrium to favor the formation of the desired alkene. So synthesizing a Wittig reagent. A given Wittig reagent is synthesized in 2 steps from the corresponding alkyl halide. We have this phosphorus triphenyl. You can just imagine, I don't usually draw these, but you have these phenyl groups, right? So this is an SN2, so it's a concerted reaction. Now we have a phosphonium salt. We take this is a good carbanion. And now we have our Wittig reagent, where we have the negatively charged right here and the positive charge right here. And then we can go, I want to just go back right here. Then we can take that and react it with a ketone. So once we form our Wittig reagent, we're now ready to form, react with a ketone to form the double bond. And the double bond will be a carbon-carbon double bond, not a carbon-oxygen double bond, as can be shown right here. So it says a Wittig reaction is particularly useful because it installs a carbon-carbon double bond at a specific place at the carbonyl carbon. And the Wittig reaction is stereoselective. So using a Wittig derived from a simple alkyl halide, the Z alkene is favored. See, Z means the same side. So we're getting rid of this oxygen, we're exchanging it for a carbon. It says, but if the Wittig reagent contains an electron withdrawing group, okay, we have electron withdrawing group right here. The E alkene is the major product. So it depends on what type of group that you're putting on here. Here's another electron withdrawing group. It's going to draw the electrons back. So you can kind of think, this group we can kind of play around with right here. And we can, drive it either to the E or the Z isomers. And HWE, I don't know if we discussed this. This is just Horner, Wadsworth, Emmons reaction. So Horner, Wadsworth, Emmons. That's what that abbreviation stands for. Oh, they say it right there. But if the Wittig reagent contains an electron withdrawing group, the E alkene is the major product. An electron withdrawing group or phenyl group delocalizes the anionic charge of the Wittig reagent, stabilizing it. We went over what the abbreviation was. The HWE reaction employs a reagent similar to a stabilized Wittig reagent and also yields E alkenes as a major product. So here they give an example of the HWE reaction. We're going to get the major product. We get the E isomer. See the R, they're on different sides. So HWE reagent gives the E alkene as a major product like a stabilized Wittig reagent does. So choice of solvent and use of Lewis acids can also affect the stereoselectivity of Wittig and the HWE reactions. Remember, HWE stands for Horner, Wadsworth, Emmons. Horner, Wadsworth, and Emmons. Just the people that discovered the reactions, who that is. And they talk about retrosynthetic analysis reveals two possible routes to make a given alkene via Wittig reagent. You have two different routes right here. If you were in which route is better, consider the alkyl halide needed to make either of these Wittig reagents. So route 1, they use a methyl halide. Route 2, as primary halide is needed. Because route 1 is better since the SN2 reaction with the methyl halide is better than with the secondary halide. The retrosynthetic analysis reveals 2 possible routes to make a given alkene via Wittig reagent. The overall synthesis via Wittig reaction is this. Please note though, so in each case, the first step in the preparation of the Wittig reagent is an SN2 reaction with phosphorus triphenyl. And we expect that the methyl halide will be more reacted towards an SN2 than a secondary alkyl halide. But also note that the CH3I is the preferred version of CH3X. So remember we were talking about CH3X. This is just a halide. This is a preferred version since this is liquid at room temperature. If you're using CH3Cl or CH3Br, these are gases at room temperature. So, you want to go with something that's a liquid. Otherwise, you'd have to push the pressure down, or you'd have to do some other special circumstances to make this reaction go. So that's why they show iodine right here, because iodine, this compound will be at room temperature, it will be a liquid. With the chlorine, with the bromine, these are going to be gases at room temperature. You could always cool it down, but then maybe your reaction doesn't go either. So then they go into the Baeyer-Villiger oxidation. So it's an oxidation, an oxygen is inserted into an aldehyde ketone between a carbonyl carbon and neighboring alkyl group. And you can see this right here. So an aldehyde or ketone, so in this case, the ketone, is converted into a carboxylic acid or an ester. In this case, it's an ester, right? This is your ester group. And then they go through how the mechanism takes place. You have a nucleophilic attack. So the perioxy acid functions as a nucleophile and attacks the carbonyl group. Okay. Then we have a proton transfer. The proton is transferred from one location to another. This step can occur intramolecular. Intramolecular means within the same molecule. Inter would be 2 different molecules. So intramolecular because it would involve a 5-member transition state. Then we have a rearrangement. So the carbonyl group is reformed with simultaneous migration to alkyl group. And we get these products. So the perioxy acid right here attacks the carbonyl group of the ketone given an intermediate, then can undergo an intramolecular proton transfer. And this is 2 successive intermolecular proton transfer steps. It says the rearrangement produces an ester. So in much the same way, treatment of a cyclic ketone, so now let's go to a cyclic ketone right here. We get this lactone. So this is called your lactone group. So for an aldehyde or unsymmetric ketone, the rate of migration is as follows. It says use this trend to determine regioselectivity. So they give you an example of here. So in this case right here, let's just look at this case right here. The oxygen atom is inserted on the left-hand side. Okay, we can see the oxygen atom inserted on the left-hand side of the carbonyl group rather than the right side. And this occurs because the isopropyl group migrates more rapidly than the methyl group during the rearrangement step of the mechanism. The migration rates of different groups or migratory aptitude can be summarized as follows. And they summarize this right up here. In this example right here, a hydrogen atom will migrate more rapidly than a tertiary alkyl group, which will migrate more rapidly than a secondary alkyl group or phenyl group. So below is one more example, so that's why we're putting it to the right-hand side right here. So then they come into the synthesis, the study of synthesis strategies. Is there a change in the carbon skeleton? You know, is there the first question, is there a change in the functional group? It says one of these reactions will be needed when the carbon skeleton is changed. So we've only seen, so in this chapter, we've seen 3 carbon-carbon bond forming reactions. We've seen the Grignard reaction. We've seen the cyanohydrin formation and the Wittig reaction. So that was our carbon-carbon bond forming reaction. So for our carbon-carbon bond forming, we've seen the Wittig. We've seen the Grignard. And we've also seen the cyanohydrin formation. So for bond breaking, I don't know if they show this or not, but for bond breaking, now breaking this bond right here, we've seen the Baer-Villiger oxidation. Now I'm gonna draw out, you know, and then we'll put what it is. So we have that going with RCO3H. So the carbon, that carbon got busted right there. We have this. We call this the Baer-Villiger. So these are CC bond forming, carbon-carbon bond forming. Here we have bond breaking, don't we? We're breaking the carbon-carbon bond. So steps in proposing a synthesis, you should be able to make a list of products that can be made from aldehydes and ketones and identify the reagents. Spectroscopic analysis, IR signals, so strong peaks for the carbonyl stretch. We see that right here. Aldehydes also give weak peaks around 2700 to 2800, 27 to 2800 per centimeter for the CH stretch. So increasing ring strain increases the wave number. You can see it went from a 6 to a 5 to a 4, and we increased the wave number. So aldehydes give a weak absorbance around 2700 to 2800 for the carbonyl CH stretch. You see that right here. I should have just put, this is the CH stretch right here. This is this going on right here. That's all due to the aldehyde group. So you have this right here. You're going to see that right here. This right here, you're going to see that right there. So now they talk about proton NMR. So protons neighboring a carbonyl are weakly deshielded by the carbonyl group and appear +1 ppm downfield. Aldehyde protons are strongly deshielded around 9 or 10 ppm. They're showing that right here. So these would be protons neighboring. You know, I guess this 5 right here corresponds to these 5, right? You have a multiplier here. And these protons here, these ones closest are most likely this one, and we have these here. Then they go into carbon-13. So remember carbon-13, this is 6 protons and 7 neutrons. So carbonyl carbon produces a weak signal near 200 ppm. We see that carbon right here. And the signal can be identified with relative ease because very few signals appear that far downfield in a carbon-13 NMR spectrum. So then they give us this. So reaction 1 is the hydride formation. Reaction 2 would be the acetyl formation. Reaction 3 is a cyclic acetyl formation. Reaction 4 is a cyclic thiacetyl formation. Reaction 5, remember Raney nickel is aluminum nickel. This is the desulfurization. 6 should be the amine formation. 7 is your enamine formation. 8 is your oxamine formation. 9 is your hydrazone formation. 10 is your Wolff-Kishner reduction. 11, this is a reduction of a ketone. 12 is your Grignard. 13 is your cyanohydrin formation. 14 is your Wittig. And 15 is your Baeyer-Villiger oxidation. And this can all be found on page 887. So if you want to have some help identifying all these numbers, please go to page 887. So I think we're gonna stop right here for today. We'll pick up on the homework on Monday. So you're free to go. It was a great lecture, and I look forward to the next lecture.